Welcome viewers. As a part of a genome informatics course in the School of Electrical Engineering, University of Belgrade, we had a assignment to make a comparison between different variants of the Booyer-Moore string searching algorithm. In this presentation, we'll go over the Booyer-Moore algorithm itself. We'll see some heuristics it uses. We'll also look at the structure of our project, and we'll look at some performance analysis data. For those who are unfamiliar to Booyer-Moore algorithm, it is an efficient string searching algorithm developed by Robert S. Booyer and J. Strother Moore in 1977. A naive way of searching for the pattern in the text would be by comparing each letter from the pattern against the text and then moving that pattern by one. Booyer-Moore algorithm tries to overcome this by making as least possible amount of comparisons and trying to make a biggest possible shifts using heuristics, and we'll talk about heuristics a bit later. We have Booyer-Moore algorithm described here in pseudocode. So before the search even begins, a pre-processing is necessary. The pre-processing is done on the pattern, so the algorithm remains online. The way it works is we align the pattern against the start of the text, and until we reach the end of the text we try to match the pattern with the text, and if match or mismatch occurs we make a shift depending on the heuristics we use. The first heuristic we'll be discussing today is the good suffix rule. There are two kinds of this rule, the weak and the strong, and we've decided to implement the strong one here. The way this works is on the mismatch we take the already matched suffix in the text plus the currently mismatched letter and try to find it in the pattern. If such occurrence exists, we shift the pattern so it aligns against the said suffix, and if no such occurrence exists, the pattern is shifted until it passes the current position of the last character in the text. The other widely known heuristic is the bad character heuristic. This one is even simpler than the good suffix rule. The way it works is we make comparisons between the text and the pattern, starting from the right to left, and on the mismatch we try to find the mismatched character from the text inside the pattern, and then we make if such occurrence is found, we shift the pattern until it aligns with the mismatched letter or until it moves past that position. This one here is essentially a variation of the bad character heuristic. The main difference is that here we only take a look at the last letter of the part of the text we are currently comparing, and on the mismatch we try to find that letter in the pattern starting from the second to last position. The main advantage of this heuristic is that the complicated pre-processing necessary for the good suffix rule is eliminated, and since we are only comparing the last letter in the text, greater jumps could be made than when using the only bad character heuristic. For those who are unfamiliar to Booyer-Moore algorithm, it is an efficient string searching algorithm developed by Robert S. Booyer and J. Strother Moore in 1977. A naive way of searching for the pattern in the text would be by comparing each letter from the pattern against the text and then moving that pattern by one. Booyer-Moore algorithm tries to overcome this by making as least possible amount of comparisons and trying to make. So we have to look at two cases in this heuristic. The first one is if we have a complete match or a mismatch on the last character in the text. The way it is done here is we take a look at the first letter after the text and the second letter after the text, and we calculate what should the shifts in the pattern be for those two. So if the next letter after the text, the shift of that one is 1, then we just go ahead and make a shift of 1. But in any other case, we just compare the shift for the next letter and the shift for the second letter after the end of the text, and we just make the bigger shift available. The other case we have here is when a mismatch occurs on any other letter that is not the last one in the text. So the procedure is pretty much the same here. We take the look at the first letter after the end of the text we are currently comparing and the second letter after the text and calculate those shifts. And if the shift for the first letter after the text is 1, then we take a look at the mismatch, take a look at that character, and if it only occurs once in the pattern, then we move it for the length of the pattern plus 1, and if that's not the case, we just move it for the bigger value of the shifts for the first text after the first letter after the end of the text or the second letter after the end of the text. This one here is essentially a variation of the bad character heuristic. The main difference is that here we only take a look at the last letter of the part of the text we are currently comparing, and on the mismatch we try to find that. So let's talk about the structure of the project itself. In the first picture on the furthest left we have the structure of the project divided into packages. So we have the main packages are algorithm, the heuristics. This is where all the heuristics we discussed today are located. We have performance, which is used for analyzing the performance of the algorithm, and the representation package is used to display the data we got by analyzing it. Of course, every good project needs to have a lot of tests, so we have unit and integration tests, and in the utils package we have some utilities that allow algorithm to read from the file. So if we take a look at the algorithm package, you can see that there is a base class which is abstract, and it is called the algorithm, and currently the only implementation of that class is the Booyer-Moore algorithm. Other than that, we have the utils package which contains the line feeder, and this is the class that is essentially a wrapper around the algorithm, and it feeds it the lines from a file. So the algorithm could be used both on any given string or on a file. Other than that, we have bar chart table, which is used to represent the data we've got from the performance analyzer from the performance package. For those who are unfamiliar to Booyer-Moore algorithm, it is an efficient string searching algorithm developed by Robert S. Bourne and J. Strother Moore in 1977. A naive way of searching for the pattern in the text would be by comparing each letter from the pattern against the text and then moving that pattern by 1. Booyer-Moore algorithm tries to overcome this by making as least possible amount of comparisons and trying to make a biggest possible shifts using heuristics, and we'll talk about heuristics a bit later. So in this slide, the structure of all integration tests is displayed. So we have integration test testing only the algorithm class, and we have integration test testing the algorithm class together with the line feeder wrapper and using all of the implemented heuristics. So now it's time to run the algorithm and see what data we get for different patterns and different files used. In this biggest table, you can see that which pattern and on which file it was used in each run. In the top right corner, there is a table explaining the flags used for running the algorithm. So -h is a flag for heuristic list, and -c is the flag for pattern and file list. You can see the example in the bottom left corner. So the example goes Python main py -h, then we list all the heuristics we want to use. So this fh plus sh means first heuristics plus second heuristics, so it's a composite heuristics, and then we use first heuristic, second heuristic, bad character plus good suffix heuristics, and after that we have -c flags, and then we tell it which file we want to use and which pattern we want to find. It is possible to state more than one file and one pattern here, so it is a list. So in this slide we have memory usage shown by using the improved Booyer-Moore Horse-Pull-Sunday algorithm, which is also known as the second heuristic in this project, using the composition of good suffix and bad character, using the composition of first and second heuristic, and using only the first heuristic. So from this graph you can see that all the mentioned heuristics use pretty much the same memory. The real difference between the heuristics can be seen in this slide. So this is the slide explaining how much time execution of each heuristic took. So by far the worst results has the composition between the good suffix and the bad character rule. After that, the composition of the first and second heuristic, and the best results are given using only the first or only the second heuristics, and it depends on the example which one is better in which case. So we've reached the end of this short presentation. The code itself and the documentation that follows can be found on the GitHub, and here's the link. Also, if there are any questions that may arise, you can contact us on the email shown below.